Yes. So, for a while I've been wanting to do a special series. Starting from nothing, how is it that you would be able to construct complex logical machines, uh, such as processors, memory banks, those sorts of things? Starting from the smallest atomic parts, building them out into molecular parts, such as starting with a basic memory cell and stringing them out into registers or stacks, or basic logic gates, uh, forming those up into um, components that can add binary numbers together or subtract them. Subtraction is actually very easy to do once you know how to do addition, ironically. Uh, and actually, you can do addition with subtraction by subtracting two numbers. I think. No, wait. Subtracting. Uh, what was it again? Subtracting 0 by two numbers, and then that's the negative of those two numbers, and then subtracting 0 by that negative number, and then that gives you the positive of that negative. It's kind of difficult to describe, but it works. Uh, Usually the first things you start with are the basic memory cell, uh, firstly, and what I usually do is you have one component that holds a state, no matter what that state may be. Uh, Usually a ring of uh, XOR gates acts as state storage pretty well. You're also going to want this one basic design, a monostable. See, monostables are one of the most basic designs that you're going to need. It takes any signal and takes only the rising edge of that signal as, and outputs that. And so it normalizes any signals that come in. And what that allows is for you to have a much more reliable input. So taking a look at this, you see sending a one-tick pulse to all of these XOR gates swaps all of their states together, and since they're in a string that feeds into itself like this, they keep each other on or off. And that's how you make a basic T flip-flop. And look at how fast it is also. Yeah, that's pretty good. And then what I also like to do is color code these so that you can have blue be the input color standard. So that's what you put all of your things into. And then yellow can be the standard output. And so if you were to abstract it like that, this system would take one output, which is any signal, and on the rising edge of that signal it would flip its state. And its state can be exported by this thing here. This is not a very compact design. One good idea is to actually turn this into a more linear, streamlined piece here. And typically it's also good practice to have this wired like this so that there's only one input instead of two that need to be remembered. Although the one drawback of this is it adds one tick of latency, so that's another thing you need to be aware of. And at times even wary of. There. Now this is correct. This is one T flip-flop memory cell constructed out of 6 gates. Now this gate is just an abstraction layer, so you can do this with 5 gates. And if this XOR gate were able to feed into itself normally under ordinary circumstances, then you would only need this one instead of all of these, which would cut it down to 3 gates. And if you didn't need to normalize your input to the rising edge, if you're always only receiving single tick pulses anyway, you wouldn't even need these 2 gates. and so you could have a one gate memory cell. However, it's good practice to leave this monostable in for systems that are not so normal. Although, thinking about it, it may be a good idea to have it be a standard that to assume that a system will have one-tick pulses as signals only. Now that could be dangerous, but it could also be very profitable. There, and now here we have our memory. Actually, it's a good idea to put this facing outward like this, so that you can see it from outside when you're stacking these vertically and horizontally. Makes things much easier. There. And so that way the monostables will be affixed to the outputs instead of the inputs, which in some cases I think would complicate things, in other cases would simplify things. So yeah, I think it should be much more conditional than all of that. And so this we can actually save as a blueprint. I prefer camel casing instead of the dashes or underscores or spaces. Not only is it more compact, it's, well, it's what I'm used to. I prefer capitalizing the first letter of each word in the string. And of course, this name is self-explanatory, so we don't really need a description. And since we already know everything there is to know about our coloring standard here, we don't need a description for that either. And so this we can replicate if we wanted to, as many times as we wanted to. And right now I'm planning on making a 4-bit register with this. Wait, register? No. Yeah, that would be foolish. Hold on. What I meant to say was a stack of T flip-flops, because for a full register, not only do you need what was it? Not only do you need there to be this stack of T flip-flops, you also need a special handler that I usually clamp to the top. I'll show you. This. And so, whenever this receives an input, it will export all of these into here. And usually, at the same time, I also have a resetter somewhere in line with these that also receives from here, but also receives from one of these and resets the entire set, which, yet again, hard to explain. I'll show later, though. And so in this situation, you can have these here. Imagine this is your data bus input, where all of the information flows throughout your system. And then up here we have the import signal receiver. And I'm just going to affix a monostable right here. There, and you can see the indicator. Oh wait. I think this is a yes. I accidentally included a flaw in the design. I'll fix that later. But now you can see we can select which bits to flip and then flip them at any time. The problem, however, is that we're only flipping them and not setting their state. In a normal register, this would stay on instead of being flipped over again, because it's not a T flip-flop, it's a D flip-flop we need. And so, using a T flip-flop as the heart of the design. Also, I'm going to need to update that. What we also need is a resetter somewhere in here. And that will take the state of one of these and at the same time feed back into this here. Also, this needs to be an OR gate now. And that must remain an AND gate. There. Actually, red is a good color for this because it wipes the cell in all cases. Actually, no, white would be much more explanatory. So, in this configuration, oh yes, on top of all of that, this needs to be held low, otherwise, because it's an AND gate, you know. And so now, hold on, this needs a monostable. There. Now things can get pretty complicated, although they're supposed to get complicated. Simple machines can only do so much. So now, regardless of which state the bit is in, this input wipes it and doesn't set it back on, which is exactly what we needed. And so then for the input importer here, this pin, this would be wired to both of these so that it would reset the cell and then import the new state, and that would be a full D flip-flop. Yeah, this is not stable in its current configuration. This is a temporary blueprint I'm going to use just to hold this one piece here. And so now I can stack these on top of each other to form a real register. There. Much more advanced than this already, since now it has capabilities for wiping everything held within. And so now there should be one pin for receiving new state, and there's also the option for having one pin that unconditionally wipes everything, which is probably something you would like to have eventually, or perhaps not. I'll leave that out just to keep things from getting too complicated. Actually, hold on. I've just encountered a problem. This OR gate here needs to not be an OR gate anymore, because in order for it to keep signals from interfering, yes, it needs to be an AND gate. However, it also contradictorily needs to be an OR gate because it also needs to take in this signal here, which complicates things quite drastically. So, starting with what we know we need to do, this needs to be wired to all of these in order to function. There. Usually purple I consider to be a modifier, input or output, and red also to be some kind of auxiliary or auxiliary. Uh, and then typically it would need to be wired to all of these, but that wouldn't work. Instead we would need to have another row of gates here for the control, which I don't prefer. See, this adds a lot of latency. There. And now... I think I know what's wrong. Yes, ugh, I see the problem already. So, this signal and this signal are reaching the memory at the same time, which means that they're blocking each other out. They're jamming each other, to be precise. So one thing I could do, per se, is just delay this signal by one, which is even more latency, which we prefer not to have, but in this case, theoretically necessary. There. And now... Wait, no. This also needs to go back with those. There, and now it should work. Yes, now it's functioning as a register. However, this is not ideal, as I'm sure you're aware. This has a lot of built-in redundancy, since the XOR gates cannot self-wire, as far as I'm aware. And this clamped-on piece here is only here for delay purposes. And if it wasn't for the problem of, well, I could go on. In fact, I'm going to save this as the new register for later. We can improve the design later. Right now is not the time. There. That's all the inputs and outputs necessary to be remembered. There, a 4-bit register. This is now obsolete. There. So this is one piece we're going to want to have, and we can actually tile these horizontally now in order to form banks of registers, or even whole RAM. But this is only 4 bits currently. Now, we have our memory. Another thing we're going to need is our processing, things that go in the ALU, like addition, subtraction, multiplication, and logic, or XOR, NOR, and also parity checking for branching operations, so conditional functions. I don't think we need these anymore. They're somewhat semi-vestigial, and we can replicate them at any time. Very simple. We really only want to save the complicated components. And now, for addition, which is really the primary thing we're going to want to worry about since we have all the regular logic right here we need. The way addition works is, typically with full adders, and those are made of half adders, and those are made of logic, basic logic. Later on, we can talk about more complicated ways to add numbers, but for right now, I'm pretty sure this configuration or something similar is what we need. Although we should start with the basics. So, for a half adder, we want to detect. Yes, look at that. So imagine these are both the first bit in a string of bits. So this one right here, and then this one is the second one here, that's the carry out. And so if there are, this is the first bit of the first number, and this is the first bit of the second number, and this is the first bit of the output and the second bit of the output. In fact, this configuration is confusing. I really want to fix this now. There. And so, yes. And then the carry out from that, we're going to need to bring to the second one up here. Is that right? Yeah. So, the first adder in this chain can just be a regular half adder, or it can be a full adder if you want a further carry into the whole system. Usually it's preferable to have it be a full adder, since sometimes you want to do add with carry, like in arbitrary length arithmetic, which is basically just storing a number across multiple bytes, which is usually necessary for more complicated operations. I forgot exactly how to make a full adder since it's been so long. So, carrying out. Yes. So, there are two cases in which we should carry further, and that is, so this is acting as an input, but these are also acting as inputs. So, technically, by logic, if any two of these inputs are active, we want to carry out. And this is not the most compact way you can do this either. Yes, and so that's functioning correctly. This is the, oh yes, this should probably go here as well. Oh wait, there already was there, never mind. So, yes, this is, the logic is functioning here. So allow me to just abstract things to make it easier to see. So, adding 1 to 1, that's 2 in binary. And then adding 2 to that provides 4. Taking 1, that's 3. Yes, this is correct logic. And so this is already functioning. This state can be exported into the next one of these in the chain. I really don't like how many AND gates are right here, though. I think I remember at one point being able to eliminate most of those, though. Although that's optimization. We don't want something optimal quite yet, we just want it working. And currently this is working. I'm actually going to leave this demonstration for later since it can get a lot more complicated. And now I'm going to think about control logic. Every system needs the ability to control itself. Otherwise, what is it even doing? And the first control logic you should probably think of is decoders, which in this case I mean binary to unary decoders. At some point you're going to need to detect combinations. And I'll show exactly what I mean by that. So with this decoder, I can select one of 4 possible combinations by using a number as an input. And so each number has one special output designated just to it. And so with this you can, for instance, in a processor send in an address to this number input, and in the output it will select one particular register in the memory using the register's address. Or another instance is, well, it's just for selection mostly, but also for some basic other things. Typically a 2-bit decoder is almost useless. 4 bits is probably the smallest you want to have, and is also probably the largest that's practical to use, which is why I use them so much. And this is how long a 4-bit decoder is, since for each one of these inputs that you add, you double the output, so it can get very long very quickly. There. And most of this is just tedious wiring. And then at the end, we can just save this as a blueprint and reuse it whenever. And for things like this that do have a definite significant bit, sort of a directionality, a handedness, you should almost always, well, if you can help it, you should always label which bit is the least significant and most significant. Otherwise, you can accidentally flip numbers without knowing. And in the output, I'm just going to mark the correlating outputs. And darken the things that aren't necessary to know about for the end user. So one interesting thing actually is how when wiring these there's a pattern. This bit wires to every other, this bit wires to every 2, and then off every 2. This is 4s and this is 8s. And so for this one, it should be in the off state for the first 8 and the on state for the second 8. And so it's the same pattern of alternation, but the size, the scale of the pattern doubles with each bit added to the input for a very esoteric reason, but also a very simple reason. So for this last bit, all of the outputs should be on, and for the first bit, all of the outputs should be off. And it's very important that you don't miswire anything, because that could destroy your design, and you'll have a very hard time debugging it, because it's a nest of wires, and you can't tell what's where, or what's what even, because it's just a mess. and so usually I prefer to go slowly as to not destroy everything. Yeah, now you probably see why I picked 4 bits instead of even 5 bits, because with 5 bits we would need to do twice the wiring of this, and with 8 bits that's doubling 4 times from this. So that could, hold on, I can actually show you. So this is 16 outputs, double that once to 32, and then double that once to 64, so that's 2 more of these beams. And then double this, and then double of the output of that. And that's the size of your 8-bit decoder. Because what's the maximum value 8 bits can hold? That's correct, 256. We would need 256 of these outputs. And wiring each one of those would be not only very dangerous because you could miss any one of them at any point and not be able to know about it until much later, but it's also just a pain. This is what life is reduced to as an electrician. And imagine larger projects that are more than 4 bits. This requires maximum concentration. There, now it should be complete. Usually, now is a good time to just debug the design to make sure. Yes, this is correct. That is incorrect. Why is that incorrect? Oh, hold on, I forgot something. Yeah. Starting from here, I think. Is that correct? No, starting from here. And also, actually, there, now it's complete, I'm pretty sure. Yes, it's complete. Debugging is always the scariest part. So this is one complete decoder. We can save this. I prefer to abbreviate things as much as I can so that the names don't get so unwieldy. And so now this can be used later also. We already have two functioning components. We can use at any time. In fact, these two we can use together to make a bank of registers that can be handled with addresses. So we can have this be the address selector, which routes the data to any one of these registers, and from it also. So we can use control logic to handle all of that. This is still an enigma, but fortunately there's a reason I did this first, because guess what this can do? Technically, this can add two 2-bit numbers together, because since it is a decoder, it can account for every possible combination of inputs and give one output per each. And so because of that, now you see this is the first number input, and then this can be the second number input. And here we're adding 1 to 1. Here we would be adding 1 to 2. So that would be 3. And the next one over from that, we'd be adding 1 to 3, so that would be 4 actually. What is this? Another... Oh yeah, hold on, I can update this. Guess what I missed? This. There, now it's like the problem never existed in the first place. Already functioning very similarly to an adder, isn't it? And there's only a few more inputs left to account for. Yes, and this one. And this one. So this is the standard output and this is the carry out, which can go into the start of another one of these, actually. Although, for a really good one of these, you would probably want a 5-bit decoder, but we already know about those. What was I doing again? Oh yes, so this goes to these two. This to here. This to these two. And then the final one, I already know where that goes. That goes to these two here. There. A fully functioning 2-bit adder made out of a decoder. Which is basically the same thing as this, but faster, since it processes all of the possible combinations in parallel and then gives you the correct answer at the end. Which is very inefficient in terms of processing power usage, because most of your processing power you're wasting on incorrect answers. However, it's very efficient in speed, which is one of the things that's a big problem in most cases, in terms of things like latency, or uh, also, now what's the other one? There's latency and there's, oh yeah, a different kind of processing time that cannot be overridden. I'm not sure how to describe. But these two have identical functionality now. Actually, I should save this for later. There. Actually going to leave a copy of that over there for memory. This thing we can talk about later. We can make really compact, but it's also going to be very slow. What else is there? Oh yes, another component we're going to need eventually is a clock. So a computer doesn't know to do things by itself without some kind of initiative. And in this case we can use this, and just a normal clock. There, and look at how fast that pulses now. Technically it pulses as rapidly as possible. So, one way to tell. There, you can hear how rapidly it pulses. I don't even know how to measure that in hertz. Technically I could probably use monostables to cut the signal in half so many times that I can measure more accurately. In fact, that would be fun to see. Hold on. Oh wait. Never mind, it's not monostables. It's T-flip-flops. I don't want to bother bringing those in right now even. So never mind. But also, you're going to want to have a way of controlling this. So, you're going to want to have an off switch and an on switch. No wait, an on-off switch. There. So, by default it should be off, but you should be able to turn it on at any time. And so this is a regular clock. And usually a good thing to attach to a clock is a sequencer, which just basically does things in a sequence. So one thing after another in a line, although that's usually something you attach to individual components, not the main clock. The clock, yeah, you usually put somewhere in the control logic centrally so that it controls all the vital functions. Think of it like a computer heart. And so the entire computer functions according to the beat of its own heart, per se. There, and this is how it would function with inputs and outputs. I can save this for later also. Actually, I just had a thought. This is inefficient. Mm, I don't like vertical designs. It's very, very unstackable. Hold on, let me just, I need to flip this. And actually, this also works. It's very hard to get something under them once you've decoupled them from any kind of board. There. Now, this is inefficient. Instead, what I should have done is have a dual input and output. By that I mean, there, I can just enable the output of this at any time. Although I don't like how this is processing all the time, so it might actually be a good idea to have this be here anyway. There, and so now, look, the excess signals don't leak out. Is this even necessary though? Probably not. Probably overly complicating things by adding that extra feature. Should probably just put all of these in storage when I'm not using them. So this we can build out into a cache or a RAM or anything like that. Solid state memory I don't think is possible, and in addition to that, platter drive is, I think, the only way to store information across instances. It's the only persistent way to store memory, since you have the ability to write but not the ability to rewrite using the spud guns and cardboard, since you can't place cardboard non-manually, which is, I think, a very large design flaw. And so you can only write once to any one sector, and then if you need to write over a sector, you basically need to install another platter and then write to that instead. So we have our volatile memory here, we have our some of our control logic here and here, and also some basic processing here. And at this point, what would be the best thing to do? I'm having a hard time thinking of what to do next, which is a common problem actually. Don't be concerned by that. In instances like this, I like to draw a diagram to help think. Over here I should do that. Yes. And so currently we have the general goal of an entire functioning processor. And that's the highest abstraction layer. One layer down from that we need the control. Going to color code that with blue. We're going to need the processing in red, and going to need memory in yellow. And in memory, this division, we're going to need RAM, definitely, and a way of importing and exporting memory to a larger bank. That's necessary for extensibility. regular data lines I'm going to color code white. And so if you don't have this set up here, you can only ever do anything within the confines of what you can fit in here, which is definitely not ideal. The control is going to need direct access to everything in the entire processor or computer or whatever it is. It doesn't need to necessarily be any one of those things in order to be its equivalent, its equal. For processing, we're going to need an input-output here, or we could directly input-output with memory. We could have memory addressed I/O, which is actually one thing I did a long time ago, how I did that, although that's probably not a great idea in a long term, since, well, let's just say that's inefficient for more advanced applications. Control shouldn't be completely isolated from the outside. It should only have windows to the outside from these two, or at least in our case. And so, beginning to look at things more closely, we can determine that we will need external memory bank at some point, which preferably is modular so we can detach it and reattach another one later. So kind of like a disk drive, almost, but also not entirely. And then output here, which at some point we're going to want to have, actually we're going to need to have a user interface. And so that's another thing we're going to actually need to think about. Going to need a visual portion, an auditory portion, and the actual input, which I think should be a keyboard to begin with, since that is the most simplistic way of inputting information into the machine. Auditory I don't think is entirely necessary to begin with, so we'll backlog that. And so what we are left with is a basic terminal interface, which is probably the best thing to do to begin with. Actually, the simplest thing to do is just to have a switchboard and then a set of blinking lights like the original computers, the the vacuum tube computers. However, that's not preferable. Yeah, that's very un-user friendly, and I don't like it. With this, we're actually probably going to need some kind of basic operating system also, which will be run from the boot sector of the memory, which we'll need to actually figure out also. In memory also, we're going to probably like to have a hardware stack memory, which is a lot easier to handle than a software stack that requires a lot less processing power to deal with. On top of that, I think that's actually all the memory we're going to want to have. A handler for I/O of memory, the extensions. Going to want to have RAM, the basic RAM, and optionally a stack. So that's pretty simple. In order to know what we need the control to be like, we need to know what our processes are going to need to be like. And for that, we just need to think about the very basic terms of what a computer needs to do. It needs to do logic and math. So that's typical ALU functions. But it also needs branching, so the ability to detect numbers and make decisions based on exactly what it's finding. And we're also categorizing logic as being fitting within the realm of numbers. Since you can perform logic on numbers, it just simplifies everything. So that would mean that our control unit would need to be able to read a script from memory and perform according to that script. Optionally making decisions based on what it finds in memory using the ALU, performing operations using the ALU on memory. So actually the memory is the foundation of everything in the processor. Everything functions according to the memory. And then everything else is just built-in functions that are required for any operations on memory. The basic bare minimum we're going to need for the ALU is branching and basic logic. I think a NAND gate is practically the minimum we need, but if we were to do NAND gates only, then we would also need to be able to select specific bits only instead of whole numbers. Yes, that would be too complicated, I feel. Another option is to only have subtraction, which makes it so that you can do basically anything you want with numbers, but then logic itself becomes kind of difficult to do with math. Since it's a higher abstraction layer, you'd need to use workarounds and things. So instead of that, what about every logical operation, all the primaries, such as AND, OR, and XOR, and NOR, but also addition and subtraction, and so that would be 6 operations, and then the 2 other remaining operations, which would make 8, which is a good power of 2 number. Now we could have branching be one of them, and then another one be a bit shift. Actually, bit shifting would solve the NAND problem, but we're beyond that now. Bit shifting is a very powerful logical operation, and all it really does is double and half numbers. So now we could write all of this down, but that's probably unnecessary. So looking closer at the control unit itself, we're going to need a clock, some kind of built-in ROM that tells it what instructions are supposed to do what, which I think we might want to be able to swap that out at any time later with a different ROM so that it can do different things if we wanted it to, or we could just rebuild it later. It might be too modular to include a detachable ROM for its instruction set. Probably also going to want to have some kind of a sequencer in the control unit to make sure everything is happening in order instead of there being chaos and anarchy. I'm going to need very basic memory registers for inside the control unit for storing very temporary memory of things like the effect, or I guess the output of a branch operation, and importing numbers for branching, just normal things like that. This is in essence a more complicated version of just a Turing machine, thinking of memory as being somewhat like a tape reel. It's all very, in essence, very simple and primitive, but in application it needs to be more advanced in order to be practical to use. Actually, this we can exclude from this abstraction layer, since this is only looking at inside here. And we already know what the 2 of these are supposed to be like. Actually, should we take a look deeper into this part? Yeah, probably. So, in here, we're going to need the arithmetic somewhere, the logic also. Branch detection at some point, which actually I like to have an ALU built into, an accumulator built into the ALU for storing temporary data right here, and we can attach the branching directly to the accumulator just to see what is in the accumulator and if it is something specific, we can make a decision based on that. And then the logic and math can be affixed directly to the accumulator. And then that we can have importing and exporting by one or more buses outward. And then this we're going to need to have a control bus or just a control line even to and from the control unit itself. These we're going to need to control with the control unit. So actually, control line should be coded blue like that. And so this is the basic structure of our ALU. Yes, no more complicated than that really. So, uh, for importing and exporting, we might want to have some kind of a fixture here, this being controlled also. There. That looks correct. So that would be the ALU, which this is basic enough, I think. The RAM is, I think, self-explanatory. It's a very basic component. And then the control unit is really all that's left that's even that complicated enough to talk about. So within the control unit, we're going to need a clock to run everything. Branching from that sequencer, we're going to need at some point a kind of decoder for decoding instructions. We can place that somewhere. I think up here would be more space efficient actually. Get rid of this because we don't need it anymore. We're going to need memory for importing things and also exporting things. Registers for control. Probably space those out more to leave more room. So, a register to take instructions from outside. A decoder to decode what those instructions should be. And then, based on that, it should send control signals outward to the components. Or should each component have its own instruction decoder and the instructions are only held in the control unit temporarily? But either way it works, the sequencer is going to need to... Wait, no, the program counter I'm forgetting. At some point we're going to need the program counter, and for that we're going to need branching to control that. We're going to need the sequencer to control the program counter, which technically is its own register, which increments occasionally. And then that's going to control addressing. So that's going to iterate through the program and perform actions according to the program. Oh yes, and of course I think we're going to need a pass-through here for... Hold on. I just keep trying to make this less just horrible. Yes, a pass-through here for... Yes. So usually I like to have it so that in each instruction there's one operation followed by one address, and the operation would go through to the operation decoder, and then the address would go directly to the output here for addressing a part of memory to perform the operation on. And so in this way program memory can coexist with variable memory. Now this is very primitive actually, beginning to notice. Oh yeah, the reason we need a decoder for instructions in the control unit itself is because it itself is a component that needs to be controlled. this program counter needs a way of jumping to somewhere specific in the program, and the only way it knows to do that is if it receives a special instruction to do so from the memory. So actually, the memory is controlling the control unit, and the control unit is controlling the memory. It's not really a true hierarchy. It's more of just a system designed to function in a particular way. At some point, I think we're going to need this to go to a power button on the front of the computer. Also, sequencer is going to need to control these two registers. So this is probably what our control unit is going to vaguely look like, which is a lot more complicated than the ALU, I think. Yes, so this line is going to go to memory for addressing, and this line is going to go to the ALU for operations. And on top of that, actually, we're going to need a special control here for wait, what were I think it's what is it that I needed this for again? Oh yes, it's not after, it's before, or I think. Now what that's for is wait, what is that for? I'm having trouble remembering something very important, but I'll remember it later. Right now I think that's enough for today. Deconstructing exactly what we need to do for the future. Yeah.